During the last lecture, we proved the first variation formula, which says that if gamma is a unit speed admissible curve, capital gamma is a variation of gamma, and V is its variation field. Then we have that the length of gamma s is a smooth function of s, and its derivative at s equals 0 is given by this formula. Here I am considering the case where the variation is proper. So this derivative is given by the sum of these two terms. Sorry, this is k minus 1. And now we want to prove this very important theorem. Every minimizing curve in a Riemannian manifold is a geodesic when it is parametrized by arc length. The proof is based on the use of this formula, and it consists of two parts. The goal of the first part is to prove that the covariant derivative of gamma prime is 0 on the subintervals of AB, where gamma is regular. And the second part proves instead that the curves has no corners, so this means that the delta I gamma prime is always a 0. So suppose that gamma is minimizing, and of unit speed, and suppose that gamma is a proper variation, then Lg gamma s is smooth and achieves the minimum at s equals 0. The reason why this is true is that gamma is minimizing and gamma t is gamma 0t. Please observe that in the proof we will not use that this functional, the length functional is a minimum, but just a critical point. That is DDS at s equals 0 of Lg gamma s, this is 0. So this theorem could be reformulated as follows. Given a curve which is a critical point for this functional and is parameterized by Arclay, then it is a geodesic. Then let's observe that every proper vector field along gamma is the variation field of some proper variation. Then the right hand side of the first variation formula must be 0. That is this is 0. Okay, let's prove that the covariant derivative along gamma of gamma prime is 0 on an interval of the form ai minus 1 ai. That is the interval where gamma is regular. If we do this, then we can conclude that gamma is a broken geodesic. So on this interval we define a bump function so that phi is positive on the interior and it is 0 elsewhere. Then we can choose v to be phi dt gamma prime, and this reduces to minus integral from ai minus 1 to ai of phi dt gamma prime square dt. Clearly, if this is 0 and this is positive, this implies dt gamma prime equals 0 on ai minus 1 ai. And now we need to prove that this is 0. So we choose a bump function in a coordinate chart to construct a piecewise smooth vector field V along gamma, such that V at AI is delta I gamma prime, and V A J, this is 0 if I is different from J. So this must be true for only one value of I that you can choose arbitrarily. And in this case, the fact that this is 0 reduces to minus delta I gamma prime length square, this is 0, which implies delta I gamma prime equals 0. So this means gamma prime AI minus coincide with gamma prime AI plus. And you repeat this process for all values of A of the index I, and you get that there are no corners. So no corners. And how to prove that we have also smoothness? Since there are no corners, then you use uniqueness of geodesics to prove that the restriction of gamma to this subinterval is the extension of gamma restricted to AI minus 1 AI. Why? Because you can construct a geodesic starting at gamma AI with initial velocity vector given by gamma prime AI, and uniqueness of geodesics says that this is the extension of this, and this implies that gamma is smooth because of the restriction of gamma to each subinterval is smooth. So this is the end of the proof. And now I want to make a remark. I already told you that we did not use in this proof the fact that the curve is a minimum, but just a critical point. So what you can prove is that also the converse of this result is true if you use the fact that gamma is just a critical point. Precisely, you have that unit speed admissible curve gamma is a critical point of LG. If and only if it is a geodesic. So it is clear that this implication has been already proved. What we proved is that if gamma is an admissible curve with unit speed, which is a critical point, then gamma is a geodesic. What about this implication? This is very easy. We use again the first variation formula. Precisely, you have that if gamma is a geodesic, then you have that dt gamma prime 0 and delta I gamma prime equals 0, because gamma prime has no corners, because this is a smooth curve. This implies BDS LG gamma S at S equals 0 equal to 0. So gamma is a critical point. And now we want to answer the following question: are geodesics minimizing curves? The answer to this question is no, and we will see that this answer is instead yes if we work locally. The reason why the answer to this question is no is provided by this example. Consider the sphere S2 and consider a geodesic which is longer than pi. So, for example, suppose that P and Q are on the same meridian, and look at this geodesic here. So if the length of gamma is larger than pi, clearly this geodesic here is not minimizing. Why? Because the length minimizing curve joining P to Q is this one. So the answer to this question is no. So in order to make the answer affirmative, we have to work with locally minimizing curves. What is the definition of this kind of curves? So a regular a piecewise regular curve in M is locally minimizing if every T0 in I has a neighborhood I0 contain or equal to I such that whenever A, B in I0 with A is more than B, then the restriction of gamma to AB is minimizing. In order to prove that geodesics are locally minimizing, we need some new definitions and terminology. So suppose that epsilon is positive and such that exponential map is a diffeo between B epsilon 0 in TPM and its image then we have that the image of this ball by the exponential map is what we call geodesic ball in M. Instead, this one, under the assumption that this is contained or equal to V in TPM, such that X per P is a diffeo on V. This is a closed geodesic ball. And the exp of boundary of this ball is what we call geodesic sphere. Then suppose that U is a normal neighborhood of a point P. Remember that a normal neighborhood is the image by exponential map of a star-shaped open set of TPM. Then we can define the radial distance function in terms of normal coordinates. Then we have radial distance function R defined on U with values in R, actually R plus. Union 0, writing R of X equal square root of sum of xi square, and we have also the radial vector field on U minus the point P, denoted by delta R and defined as xi over R of X dxi. Here I am using the Einstein convention. It is possible to prove that in every normal neighborhood U of P, the radial distance function and the radial vector field are well defined, independent of the choice of the normal coordinates, and they are smooth on U minus P. Instead, the square of R is smooth on U. The reason why R is not smooth, R and delta R are not smooth at P is that in the definition of both of them there is a square root. Instead, R square is smooth also at P because when you take second power, square root disappears. Now, the key result for proving that geodesics are locally minimizing is the following very important theorem, which strangely has this name, Gauss' lemma, but it is so important that it deserves to be called theorem. So suppose that U is a geodesic ball centered at P. Then delta R, defined by this formula, is a unit vector field orthogonal to the geodesic spheres in U minus P. Okay, let's prove this result. So let Q be a point in U minus P, and suppose that its coordinates are Q1, Q2, Qn. We are working with normal coordinates centered at P. So the value of the function R is of course square root of sum of Qi square, and we set B to be this number. Then if we use this formula, we get that delta R at Q is given by Qi over B delta Xi at Q. Now let V be a vector in TPM with Vi equal Qi over B. So this means that the components of this vector are the same as delta R and Q. Now let's introduce the radial geodesic, having as initial point P and the initial velocity V. We know that its local representation is given by TV1, TV2, TVN. So besides the fact that gamma V0 is P, because if T is 0, we get 0, 0, 0, 0, which are the coordinates of P. We have also that gamma VB, this is exactly Q, because B is B appears in the expression of Vi. So when you replace B into this formula, you will get BVI, but BVI is Qi. So you get Q1, Q2, Qn, which are the coordinates of Q. And most importantly, what is gamma prime V at B? This will be Vi delta I Q, but Vi is Qi over B, so Qi over B times delta I and Q is exactly this vector. So this is delta R at Q. Now let's observe that the velocity vector, the initial velocity vector of gamma V has a length given by this formula. The reason why this formula is correct is that the metric G in normal coordinate at the point P is Euclidean. We work at the point P because we set T equals 0. And we know what Vi is. This is a sum square root of the sum Qi square over B square, and this is 1 by definition of B, because B is R of Q, and this is square root of sum Qi square. So gamma is a unit gamma v is a unit speed geodesic, and this implies that also this has length 1, which means that delta r at q has a length 1. Now it remains to prove that this guy is orthogonal to the geodesic spheres. So let's write delta r is orthogonal to the geodesic spheres in u minus p. Okay, this is a bit more complicated. First of all, we define sigma b as the exponential map acting on the boundary of the ball of radius b centered at 0. This is a geodesic sphere containing q. Why? Because b is r of q, and we are taking the image of a sphere in TPM having radius equal exactly to b. So clearly the representation of sigma b in local coordinates is this sum of xi squared equal to b squared. Now take w in TQM tangent to sigma b at q. If you want to prove that this is true, then it's enough to prove that w is orthogonal to delta r at q. In order to do this, we construct a variation of a curve defined this way. So sigma defined on minus epsilon with values in sigma b, with sigma 0 equal to q, sigma prime 0 equal to w, and we suppose that in local coordinate sigma s is given by sigma 1s, sigma and s, and the fact that sigma lies on this geodesic sphere means that the sum on I of sigma I s square, this is b square. Now we define a variation gamma from minus epsilon epsilon times 0b with values in u, writing gamma st equal t over b times sigma 1 t over b times sigma n. So if you want to, you can make a picture. Suppose that this is sigma b, this is the point P, this is the point Q, then this is W, tangent by definition to sigma b, and sigma is a curve on sigma b. Then if this is the ST plane, then gamma sends this rectangle to this kind of curves. And we want to prove that delta R at Q is orthogonal to W. So if we fix S, gamma S is a geodesic, this follows from the fact that in local coordinates, local normal coordinates, a geodesic is something having the form T times V1, or let's write TA1, TA2, TAN. This is exactly what we have here. So gamma S is a geodesic. With the property that gamma S at 0, this is sigma I S over B times delta I at P. It immediately follows from this formula. And since we have this formula, and the fact that G, the metric, is Euclidean at P, then this has length 1. Implies gamma S has unit speed. Okay, so now let's study the variation gamma. And we define S as delta S gamma T delta T gamma. What can we say about S at 0, 0? This is DDS at S equals 0, gamma S 0. this is 0 because gamma s at 0 is constant. T 0 0, this is d dt at t equals 0 of gamma 0t, but gamma 0t is gamma vt. And clearly this is the initial velocity vector of gamma v, which is v. And instead, what happens at 0b? This is dds at s equals 0. What is gamma 0b? Sorry, gamma sb. This is just the derivative with respect to s of sigma s. And by construction, this is w. Instead, what is this? This is ddt at t equal b, this time gamma vt. That is the velocity vector of gamma v at b. But we have seen before that the velocity vector of gamma v at b is delta r at q. So remember that our goal is to prove that W is orthogonal to delta R at Q. Precisely, this is orthogonal to this. The idea is that we want to use the fact that this is 0 and we want to prove that this is 0 implies this is a constant with respect to t, implies S 0b multiply inner product t0b. This is also 0. That is W delta R Q are orthogonal. So it remains to prove this. But this is easy. Because first of all, we use the compatibility of the covariant derivative with the metric, and this is delta dts t plus s dt t, and then we can use the symmetry lemma to have that this term is dst t plus sdt t equal dStt, because we are working with geodesics. Now gamma s is a geodesic, which means that this is 0. And this can be written as 1/2 the derivative of this inner product, but this is 1/2 delta s, delta to delta s over delta s of the length of t squared, and this is 0 because this is equal to the velocity vector gamma s, which is 1. So this is the end of the proof. I want to mention a corollary without proof. If r is the radial distance, delta r is the radial vector field, then we have that the gradient of r coincide with delta r on u minus the length of b. Instead, what I want to show is this proposition, which says that if t is a point of M and Q is contained in a geodesic bow centered at P, then up to a reparametrization, the radial geodesic from P to Q is the unique minimizing curve. How to prove these results? So suppose that the geodesic pole is this, and by hypothesis we have that Q belongs to this ball. Then suppose that this is a radial geodesic, from P to Q, parameterized by Hack-length. So its length is 1, and suppose that it is given by this formula, where V is in TPM, and the length of V, of course, is 1. Clearly, since gamma is a unit speed curve, we have that the length of gamma coincide with this number. So in order to show that this geodesic is minimizing, we have to show that any other admissible curve from P to Q has length greater or equal to C. If this is true, then gamma is minimizing. Okay, how to do this? So suppose that the sigma is such a curve, and we suppose that it is parameterized by Hack-length. Then we denote by A0 the last time that sigma t is P and B0 in 0B, the first time that sigma t is Q. That sigma t meets the geodesic sphere sigma c of radius c around P. If we want to make a picture, the result is this. Suppose that P is this point, Q is this point. Then we have a curve joining P to Q, and which, for example, behaves like this. It starts from P, then after a certain time returns to P, then at certain time intersect sigma C, and then it reaches Q. The reason why we define A0 and B0 is that we want to work with sigma restricted to A0, B0. This is a map whose image is just this segment. This is sigma of B0. Our goal is to prove that the length of sigma restricted to A0, B0 which clearly is smaller or equal to the length of sigma, because this implies that Lg of sigma is larger or equal than C. And this is the length of gamma, and this says that gamma is minimizing. So in order to prove this, we consider the function R composed with sigma. This is clearly at least continuous. On A0, B0, and it is piecewise smooth on A0, B0. This hypothesis, this properties allows us to use the fundamental theorem of calculus and to write that this integral is R sigma B0 minus R sigma A0, which is exactly C, because sigma A0 is P, and this belongs to sigma C. So this is the distance between a point on the geodesic sphere sigma c and the center, which is C. So what is this? This is the integral of the r sigma prime t dt Now we use the following definition. The gradient of a smooth function this is defined as follows. Is df sharp. If you use the definition of sharp, you can find that this identity holds true. So let's use this formula with f equal r and w equal sigma prime t. So we get that this is equal to the integral of this inner product and clearly this is smaller or equal to this integral So now we use the previous corollary, which says that this coincides with delta r, and this is a vector field which has length 1. So this is just this, but this is Lg of sigma restricted to A0, B0, which is smaller or equal to this because sigma restricted to this interval is a curve having a length smaller than the length of the entire curve. So we prove that C is smaller or equal to the length of sigma. Now we have to prove the following. Suppose that inequality, the identity holds, then sigma is gamma. So essentially this is the uniqueness part. So remember that sigma is a length curve defined on an interval of this form. The speed is 1. So this identity says that B is equal to C, and the inequalities in my previous chain of inequalities are actually identities. So first of all, the fact that this is not smaller than this, but it is exactly equal, implies that A0 must be 0. That is the last point, last value of t, such that sigma coincide with p is 0, and b is 0 is b. This was the first time where sigma meets the geodesic sphere, and b is equal to c, is written here. This must be true, otherwise sigma restricted to 0A0 and sigma restricted to B0B would give a positive contribution to this length, which would be larger than this one. Now, from this identity, from the fact that here you don't have the inequality, but you have the identity, you get that sigma t is parallel to gradient of R along sigma t, but this implies that they are equal Why? Because this by hypothesis has length 1. It's written here. And this one is delta R along sigma t, which is a vector of length 1. So this must be true. So, conclusion, sigma and gamma are integral curves of delta R. This sentence means that the velocity vector of these two curves is delta R, and they pass through Q at the same time. T equals C. So we have that they are equal. And this is the end of the proof. I want to mention two corollaries. Of which I will not present the proof. The first one says that within every open or closed geodesic ball around T, the function R of x coincides with the Riemannian distance from P to x, and second, in a connected Riemannian manifold, every open or closed geodesic ball coincide with an open or closed metric ball of the same radius, and every geodesic sphere coincide with a metric sphere of the same radius. The meaning of this second corollary is the following. This says that exp of b epsilon 0, this is a set of points in M such that the distance with respect to the metric G between P and Q is smaller than epsilon. Exp b epsilon 0 closed, this is Q in M such that the distance is more or equal than epsilon, and exp of this is Q in M such that the distance is epsilon. Okay, let's stop here. Thank you.